This is the third lecture in this course on fluid mechanics. Today I'll be talking about hydrostatic pressure. The learning objective is to understand how the pressure in a fluid relates to its depth. Before discussing pressure in the context of fluids, let me first start by giving an example of it in the context of classical mechanics. For those of you who have not yet studied classical mechanics, this example will hopefully make the concept of pressure a little easier to understand. So what is pressure? Pressure is a measure of how concentrated a force is. Mathematically, it's represented as force divided by the surface area through which the force is acting. Let's look at two situations. In the first, a 50 kilogram weight is resting on a table. In the second, a 50 kilogram weight is resting on a small wooden block of negligible mass, which is then resting on a table. The force on the table caused by the object's weight is 50 kilograms times 9.8 meters per second squared, or 490 newtons. This will be the same in both situations. However, in the left side example, that force is distributed to the table over the relatively large surface area of the bottom surface of the weight itself, and thus the pressure on the table will be relatively low. While in the right-hand example, the force is distributed through the much smaller surface area of the block, and thus the pressure on the table will be relatively high. In fluid mechanics, instead of one solid object imparting pressure against another solid object, we have a fluid imparting pressure against a solid. But the concept of a force per unit area is the same. When talking about fluids, there are a number of different types of pressure that one can discuss. The most fundamental and important of these is something called the hydrostatic pressure. This is the pressure present within a fluid when it's at rest. It acts equally in all directions, and it acts at a right angle to any surface that is in contact with the fluid. So if we have a glass of water, at a given level within the water, the hydrostatic pressure, which is a result of the weight of fluid above it, acts on the side of the glass equally in all directions. Since pressure is the force divided by area, if the pressure was somehow unequal, it would mean the forces on the glass were unequal, which would consequently result in the glass of water moving. And of course we know that a glass of water at rest does not start to slide laterally on its own. As another example of this, imagine taking a playing card and submerging it vertically into the water. The hydrostatic pressure in the water will act at a right angle to any surface in contact with the fluid. That means that there is a right-sided pressure pushing on the left side of the card and a left-sided pressure pushing on the right side of the card. As these forces are equal, the card will not spontaneously move in either direction. Keep in mind, however, that just because there is no net lateral force on the card caused by the hydrostatic pressure does not mean there is no net force of any kind on it. From the last lesson, we know that there is still the card's weight and the card's buoyancy. So unless the card is exactly the same density as water, it will still move either up or down within the water once released. Is there any way to quantify the hydrostatic pressure? Common experience might tell us that the pressure in fluid increases at increasing depth. For example, when you jump into a deep swimming pool, if you've ever dived deep down underwater, you've probably felt the pressure increasing as you go down deeper and deeper. Quantitatively, this pressure increase can be calculated with this equation. The difference in pressure between 2 points is equal to the density of the fluid times little g times the difference in vertical height between the 2 points. In the case of the glass of water here, if we were interested in the pressure at the bottom, the 2 points we would use would be its bottom and top. The pressure at the top is equal to atmospheric pressure, and the difference in vertical height is just the depth of the water. To refer back to the last lesson on Archimedes' principle and buoyancy, some of you might realize that the buoyant force on a submerged object, which we said was equal to density of the fluid times volume of the displaced fluid times g, is simply a manifestation of the difference in hydrostatic pressure that's acting upwards on the bottom side of the object and the hydrostatic pressure that's acting downwards on the top side of the object. An interesting consequence of this hydrostatic pressure equation, which may or may not be immediately obvious, is that the pressure at any given depth is independent of the shape of the container or the path that the pressure must be transmitted along. For example, I could have a collection of rare and exotic jellyfish that I want to display in my home, but to highlight their uniqueness, maybe I want to build an equally unique aquarium system in which to house them. If I wanted to know what the maximum water pressure was at the bottom of the system of tanks, the only thing that would matter is the total vertical distance between the top and bottom. The shape of the tanks, the volume of the tanks, the width and length of the connecting tubes are all irrelevant. Also notice that the lower tank needs a sealed lid. If the lid was not there, the weight of the water in the upper tank would cause the lower tank to overflow. This is an example of a principle frequently paraphrased that fluids at rest seek their own level. This means the surface of any fluid at rest will have the same height above the surface of the Earth at all points. Let's look at a quantitative, real-world example of hydrostatic pressure. We have a house at the bottom of a hill, which gets its water supply from an open, unpressurized water tank at the top of the hill. The water tank is 4 meters high and full, and the base of the tank is 50 meters above the level of the house's faucet. Given these distances, what is the house's water pressure? As we just reviewed, the pressure difference between 2 points within a fluid system is the density of the fluid times G times the total difference in height between those 2 points. So we have the water pressure in the house's faucet minus the water pressure at the very top of the tank, which if the tank is open and unpressurized, is equal to atmospheric pressure. This equals 1,000 kilograms per cubic meter times 9.8 meters per second squared times the total height of 54 meters. This is equal to 5.29 times 10 to the fifth kilograms per meters second squared plus atmospheric pressure. The units of kilogram per meter second squared is cumbersome to talk about, so this combination has been defined as its own unit, something called the Pascal, after the French mathematician Pascal, whose name has been attached to a specific physical principle that will be the subject of a future lesson. In addition, this idea of a pressure that is equal to some number plus atmospheric pressure gave rise to the concept of gauge pressure, since atmospheric pressure is essentially equal at both the top and bottom of this type of system. The gauge pressure in this type of situation is the total pressure minus atmospheric pressure. When people refer to the term pressure in most everyday situations, such as discussing their home's water pressure, whether or not they realize it, the gauge pressure is often to what they are actually referring. That's an introduction to the concept of hydrostatic pressure. The next lesson will review some of its applications in medicine.